So let's look at a couple of more examples for the alternating series test. Does the following series converge or diverge? Notice I have a negative 1 to the n minus 3, but that doesn't matter because it still creates the alternating series if I spit out a few terms. So when I put n equals 1, that just becomes negative 1 to the negative 2. And negative 1 to the negative 2 is really just negative 1 squared in the denominator, which still gives me a positive term. When n is 2, I put that in, I get negative 1 to the negative 1, which again is really negative 1, but with a positive exponent in the denominator. So I do get this alternating series going on. So I pull out my Bn, which is the positive terms only, and I have to check two things, that Bn is decreasing and also that Bn eventually goes to 0. And if I can show these two things, then I can conclude that this series is actually converging. So is it decreasing? I can do a quick check of the next term with the current term. So I have n plus 1 over n plus 1 plus 4, which I guess is n plus 5, and then Bn exactly as it is. And when we look at this to compare which one is bigger and which one is smaller, it's not, this actually should be n plus 4 for the B sub n. It's not quite clear right off the bat that this is in fact smaller than this, because if we go ahead and put in some values, we'll see that when n is equal to 1, for example, this actually is not going to be smaller than that. We can see that here because we spit out a couple of terms. It looks like this is not going to be an absolute value smaller than this guy. This is 0.2 and this is about 0.23. So it's not clear that for all n this is actually smaller than that. Because I'm adding 1 to the numerator, it almost feels like I'm making this bigger, but then again I'm also adding 1 to the denominator and doing two changes at once, so it's not clear right off the bat. We can kind of go look at our calculator and see what happens since this is not clear quickly that this inequality is strictly less than between the two of these for all n. So I've put in my sequence terms, and my calculator is in sequence mode. Let me go to window. Let's go to maybe like the first 10 terms and see what happens. And since they all seem to be smaller than 1, x, y, let's make y max 1, it's already 1. So let's go look at the terms of the sequence, and it looks like it actually maybe goes up and then goes down. Let's go look at a few more terms. Let's go to 20. Go far out and see what happens. So maybe there's a bump and then eventually it goes down. And this makes me quickly think, let me see if it even goes to 0, because if it doesn't go to 0, which is a quicker check probably, alternating series test won't even apply. But if I look at this, it looks like it does go to 0. It does satisfy the second one because the degree in the denominator is bigger than the numerator. So it seems like maybe it's increasing then eventually decreasing. If I'm looking at my TI, let's go actually use the derivative to figure out what happens here. So we will take the sequence terms, of course the Bn, after having gotten rid of the negative 1. We're going to compare it to this function and see if this function indeed will be decreasing forever eventually after some certain point. So we go ahead and take the derivative of this, apply the quotient rule, and then let's go ahead and simplify this and see what happens. So derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. I'm going to go ahead and multiply top and bottom by 2 root x to get rid of 2 root x here. So 2 root x's cancel and I end up with x plus 4. And then root x and root x will give me an x. So I have minus 2x over all this business when I multiply these two guys. Simplify the top a little bit more. So now we have our derivative as simplified as we can, I guess. And we want to show that this will be decreasing after some certain point. We know that we're looking at n being 1 and on positive, so x all positive, which means this piece will be positive. this piece will be positive anyway because it's squared. So in order for this derivative to become negative and cause it to be a decreasing function, we need this to be less than 0 or negative. So we're going to force it to be less than 0 to make f prime less than 0 negative and f decreasing for all those x values. So this inequality tells me 4 is less than x. So in other words, after x equals 4, this f of x is indeed decreasing for all x. So what we were seeing on our TI was probably up to 4, the thing creeps up and increases, and after that it is going to decrease. So if we go out to our window further, it's going to show something that's decreasing, but it's doing it probably slowly, so it's hard to tell here. So it is decreasing, which means item number 1 is checked. Bn is decreasing for all n, let's say greater or equal to 5, because it was decreasing after 4. For it to be negative, it happened after for all the x values bigger than 4, in other words. So for all n greater or equal to 5, this thing really is decreasing. Remember, we said eventually, so it applies here. Does this go to 0? That's not too bad. We did that visually. So limit as n goes to infinity of, we had root n over n plus 4. And that actually does, if I divide everybody, if I'm formally showing it, I divide everybody by the highest power in the denominator. I end up with limit as n goes to infinity of 1 over root n, because I have root n on top and root n in the bottom, so I end up with 1 over root n plus 1 over 4 over n. And if I look at the limit as n goes to infinity, this goes to 0, this goes to 0. So I actually end up with 0. So number 1 checked out for this alternating series. Number 2 checked out as well. Therefore, we can conclude that by the alternating series test, this series actually converges. Does this series converge or diverge? Well, we know it's alternating because the n is pretty obvious. When n is 1, it's negative. When n is 2, it's positive, and so forth. So I have to pull out my Bn and make 2 checks on it. This guy has to be decreasing, and also this guy has to have a limit that goes to 0. Now the decreasing one might be a little bit more work to do. The limit going to 0, sometimes visually it's easier and quicker to do. I think I'm going to do that in this case. It might seem useful. So if I take my Bn and I look at the limit as n goes to infinity, I can divide everybody by the highest power in the denominator. You might already see what this limit goes to anyway. So root n is the highest power in the denominator. And that's going to give me limit as n goes to infinity of, I guess, just 1 in the numerator. This is root n, not root 2. 1 over root n plus 2. And we can see that as n goes to infinity, this guy goes to 0. So I end up with 1/2. And if I'm ending up with a limit of 1/2, I have to stop with AST. Because AST says limit has to go to 0 and this has to apply, and then I can conclude something about convergence. So the minute the limit doesn't go to 0, stop, AST is not applicable, but it does give us a hint that if the terms in absolute value are going to 1/2, that -1 oscillating is only going to cause things to just switch back and forth. So automatically our our next instinct is I'm just going to go to the divergence test and deal with the whole terms of the sequence and pull them out of the series. So the next thing would be to just quickly go and say limit as n goes to infinity of this guy, all of it, not just looking at it in absolute value. This is going to go to a half. This is going to keep causing it to switch back and forth and approach positive and negative a half eventually. So that limit actually will not exist. So by divergence test, this guy, we can say, actually diverges. So AST sort of gave us a hint in the process, but ultimately, by divergence test, this series diverges. I don't even have to go bother checking for decreasing.